All right, so we're going to do a little review of our synthetic division here to start. So remember, we take the 0 of the divisor. So that's -2. That's what makes my divisor 0. And I write my fraction house upside down for synthetic division, just because synthetic division, we put the quotient on the bottom, the answer. Regular long division, we kind of put it on top, but I just write it upside down. In here, I put my coefficients, so that's like a 1, x cubed plus 2x squared minus 6x plus 4. Synthetic division says the first one drops down, and then what I do is I multiply the -2 times the 1, and that's what gives me this number here. So -2 times 1 is -2. Now I add the column, so I get the next part of my quotient, which is 0. Now I multiply the -2 times the 0. So then, and that will give me my next number here. So that's 0. -2 times 0 is 0. Now I add the column. So I get -6. Then I multiply the -2 over here. Again, times the -6 here. And I get 12. And then I add and I get 12 plus 4 is 16. Now, when I look at, remember that I look at this and remember that's my quotient or my answer, 1, 0, -6. That is my remainder. Okay, so there's the division. I could write this division out as this is my constant term, this is my x term, this is my x squared term. So I can write the answer out as 1x squared plus 0x minus 6 plus the remainder over the divisor. So you just did a bunch of practice on that. Lastly, I don't need to show the plus 0x, so I can have x squared minus 6 plus the remainder over the divisor. All right, so that's a review on how to do that. So next we're going to do, they want us to find out or evaluate f of -2. So that means we got to plug in -2 for x. I'm going to let you do that here so you can pause the video. Okay, so we should get 16. Right, so if you didn't get 16, it's because that has to be squared because of that squared there. Sorry, I forgot to write that down. So you get 16. F of -2 equals 16. It says to compare 1 and 2, and what do you notice? So hopefully you notice that when I plug -2 in, I get a y value of 16. That's the same thing as my remainder when I synthetic divide by that x value. Okay, so the remainder is equal to f of -2, which is the y value. So synthetic division is a tool just like addition or subtraction, and we can use it for a couple different things. This is just one thing we can use it for. It's called the remainder theorem. And instead of plugging a number into a function, we can just use it. We can use synthetic division, and that'll get us the y value. So sometimes it's easier to do this process to find out what y is going to be than to do this process. And sometimes it's easier to just plug it into the function. It really depends on the function and the number you're plugging in. So when we use synthetic division, it's the same thing as plugging in the number for x and getting our y value. That's what the remainder theorem says. So when we divide a polynomial by x minus c, so remember when we do synthetic division, we're really using c there, right? The remainder is, we'll just call it r. Based on the remainder theorem, what's the remainder of that, all right? So, the remainder is r, which is going to be equal to f of c. So the remainder is the same thing as if we plug it in. That's all that's saying, that if we do the synthetic division, the remainder will be the same thing as the y value we would get if we plug that x value in. All right, so based on that remainder theorem, what is the remainder of this guy? So let's do the synthetic division. The 0 for x minus 4 is 4. So if I plug 4 into this function, I would get 4 squared minus 7 times 4 plus 12. Whatever I get here for my remainder, that's going to be the same thing that I would get here if I simplified that number. So I think it's easier to do the synthetic division. We've got 1 for our coefficient. We've got negative 7. And then we've got 12. So the 1 comes down. 1 times 4 is 4. Negative 7 minus 4 is negative 3. Negative 4 times negative 3 is negative 12. So that is 0. So that's what we would get if we plugged 4 in there. We would get 0. All right, so that's what the remainder theorem says. It says you don't actually have to plug 4 in. You can just do the synthetic division with 4 and get your y value by looking at the remainder. All right, so another thing to remember from division is if the remainder is 0, which happens here, this means that x minus 4 is a factor of the polynomial x squared minus 7x plus 12. That means it divides out evenly, right? Like when you do long division with numbers, if you do 15 divided by 3, you get 5 with a remainder of 0. That means 3 is a factor of 15, and we also know 5 is a factor of 15. So a remainder of 0 is pretty strong. All right, so this just takes you through how you can do this on your calculator, like plug in numbers into a function instead of doing synthetic division or instead of plugging it in. We're going to skip that for now. Here's some facts we also know. Whenever f of x equals 0, then we know x is a root or a 0, right? Any x values that make our function 0, we call those roots or zeros. And we know that from like factored form. You guys should be pretty used to this by now, right? The roots or the zeros, in this case, the roots are x equals negative 2 and x equals 3, right? Because those are the x's that make our y value 0. That's what this says. All right, so we know that x is a root or a 0. So what we're going to look at now is, we don't want to go over this. What I want to tell you now is that finding roots is easy in factored form, right? That's what we've been working on. But what if it's not in factored form? For instance, what if it were f of x equals x squared minus 7x plus 12? How do you find the roots in this case? Well, you could just factor it. Put it in factored form. It starts off x and x. Negative 4 and negative 3 are the numbers that multiply to 12 and add to 7. So now I know my roots are 3 and 4. Right? I should say x equals, sorry. So that's how we put it in factored form. But what if we can't factor it? So what if you had f of x equals x squared plus 3x plus 1, right? There's no combinations of things that multiply to 1 and add to 3. Well, we could do our quadratic formula because this thing is a quadratic. It's squared. And that'll find our roots, okay? And then we can, we have our roots, which we can write our factors and all that stuff. But the question becomes, what if we can't factor it and it's a power bigger than x, like say x, power bigger than squared. So let's say x to the 4th plus 3x to the 3rd plus 7x squared plus x minus 4. How can we factor this? Well, we can cheat, is what we're going to do. We're going to look at the graph. Any x-intercepts are roots or zeros. After we cheat, though, I want you to confirm by plugging in the x to show it is 0. All right, so this rational root theorem is something else that we're going to kind of look at in a minute. But first, we want to look at just this idea here. Okay, so I want to go down to an example, and we're going to use this example to do something different than what it's asking us to do. Let's say I want to find the zeros or the roots of this thing. So I'm just going to do like a little thing up here. Example 1. We already did an example 1, so I'll call it example 1A. No, we already did a 1, so I'll call it 1B. Okay, find the roots of find those roots. So we try to factor it, we can't. The only thing we could try is factor by grouping. So like if I pull out an x squared here, I get 3x minus 2. Here there's no common factor, so I pull out a 1 and I get 7x minus 2. It doesn't work because these don't match. So I can't continue factor by grouping. So I can't factor this thing. I can't use the quadratic formula because it's a power bigger than 2. So now what we have to do is just graph it and look at the graph. So you're going to go to your calculator or Desmos and graph it. All right, so let me just take a photo of this so I don't have to keep switching back and forth on the iPad. Okay, so let's go to Desmos. Three x to the third minus 2x squared minus 7x minus 2. We should put a y equals in front of that, or an f of x equals. All right, so if I look at the graph and I start cheating, I can see that like 2's an answer, that decimal's an answer, whoops, that's not a 0, and negative 1's an answer. So it looks like it has 3 roots, because there's 3 x-intercepts there, 3 real roots. So I can show that those are roots by plugging them in. So I've got 2, negative 1, and negative 0.3 repeating. So the roots are x equals negative 1, negative 0.3 repeating, and 2. So now I want to just prove those are roots. If I can show that g of negative 1 equals 0, then I know it's a root. Okay, so and I'm not going to show this for all of them, but I want to just write out negative 0.3 repeating is negative 1/3. If I can show that, it's equal to 0. And then if I can show g of 2 is equal to 0. So let's start with g of 2. I can plug it in and get the y value and show that I get 0. Or remember, the remainder theorem says instead of plugging in, if I don't feel like doing all that math out, I can do synthetic division. So I'm going to try the synthetic division. If I go 2 and I take all these coefficients here, I got 3, negative 2, negative 7, negative 2. And I do synthetic division, my remainder will be what I would get if I plugged it in. So I drop down to 3. 3 times 2 is 6. 6 minus 2 is 4. 4 times 2 is 8. 8 minus 7 is 1. 1 times 2 is 2. Negative 2 plus 2 is 0. Confirmed. This means that g of 2 equals 0, and that means that 2 is a root. You can do that with all of these numbers. And I tell you that even doing that with negative 1/3 is better than plugging in negative 1/3 into the function. All right? So that's how we can find roots if we can't factor it. If it's not in factored form, you can look at the graph and then use synthetic division to show that it actually produces 0 when you plug it in. All right, so now there's another thing we could do to narrow down our list, and that's the rational roots theorem. So I'm going to come back to this now. So if you have a polynomial and you want to find its roots, as long as they're rational numbers, this doesn't work for irrational numbers like square root of 3 and stuff like that. But if there's rational roots, they can come from this theorem. So you can make a list of possibilities so that when you're looking at the graph, if you see a number like 0.3 repeating, you kind of recognize it from this list. So this list is just a list of possible rational roots that you can have. And it has to do with the coefficients, right? So I have my polynomial written in standard form. There's a coefficient here. There's a coefficient here of 1, a coefficient of here. But this one is the leading coefficient. Leading coefficient in this case is 1. You got to list all the factors of 1. So in this case, it's just 1. Now the constant is the number at the end that doesn't have an x in it, and the constant is 12. I know it's negative 12, but I guess we'll call it negative 12. The factors of that number are 1, 2, 3, 4, 6, and 12. I just like to put them in order. You can put them in any order you like. Okay? So those are the factors of that. Any possible rational root will be found by doing the division of those. So you're going to take the constant, the factors of the constant, this is what the theorem says, divided by the factors of the leading coefficient. Okay, so the factors of the constant are 1, 2, 3, 4, 6, and 12. The factors of the leading coefficient are 1. So I make all the possible different combinations of fractions I can with that. So I can have 1 over 1, which is 1, 2 over 1, 3 over 1, 4 over 1, 6 over 1, 12 over 1. Yeah, and so that is all the possibles, but you could also have the negative version of all of those. So there's 1, 2, 3, 4, 5, 6. There's 12 possible roots. That gives you a little bit more information when you're looking at the graph of seeing where the roots are. You kind of know going in that it should be one of these numbers if it's rational. It could still cross on the graph. If it crosses at the square root of 3, you're never going to find that with your rational roots test. It doesn't find those, okay? So there is my list. I already did that part here. So there's my list. Okay, so start testing them, and then it says, how can we do this quickly? Look at number 5 and enter the new equation. Entering the new equation, we skipped that number 5 part kind of thing, like about using the calculator. So what I'm going to tell you is just look at the graph and see which ones work on the graph. Okay, so this is x cubed plus x squared minus 8x minus 12, right? So x cubed plus x squared minus 8x minus 12. Did I get that right? Did I remember it correctly? Yeah. So if we look at the graph, sorry, I'm going to condense this a little bit. I can see it has 2 roots, and those are from our list. So when we test them, negative 2 and 3 should work. Let me show you. So here's, you want to prove it now that it's a root, right? So negative 2, and then we use our coefficients 1, 1, negative 8, negative 12. 1 drops down. And by the way, what I'm doing here is plugging negative 2 into the function and showing that it gets 0. But the remainder theorem says that instead of plugging it in, I can just do synthetic division and look at the remainder. So 1 minus 2 is negative 1. I get a positive 2. That's a negative 6. I get a positive 12. My remainder is 0. So that proves that negative 2 works. That means that f of negative 2 equals 0, which means it's a root. Let's look at one that didn't work. Like on our possible list, there was 4. Let's see what happens when I test out one. I'm plugging, so I can plug 4 into the function. But instead of plugging it in, I want to use the remainder theorem and just do synthetic division and look at the remainder. So I don't have to plug it in. It's a lot faster in my opinion. So I bring down the 1. I multiply 1 times 4. I add. I multiply 5 times 4. I add. Multiply 12 times 4. I get 48. I add. 48 minus 12 is 36. My remainder is not 0. That means that if I plugged 4 into the function, I would get 36 for a y value. So that means it is not a root. Okay? So now I can use the division of the polynomials to factor and completely and find all the roots. So for this one, I'll go off of what works. So now it comes back to the division piece. I know that basically this means I divided the polynomial x cubed plus x squared minus 8x minus 12 by the polynomial x plus 2, because remember, that's the 0 of the divisor. My quotient or my answer ended up being x squared minus x minus 6. Where did I get those from? That's this stuff right here. That's my polynomial answer. Plus the remainder divided by the divisor. The nice thing is when the remainder is 0, it's a clean factor. So that means that this part goes away. All right, so I can begin to factor this thing. That's the goal, factor that polynomial. I know it's going to be equal to x plus 2, that's the factor I divided out, times the answer I get when I divide it out. Okay, now what was this called? F of x? Yeah. So I'm on my way to factoring. Now how do I continue factoring once I divide that out? Once I get it down to an x squared, we have other methods to factor. We know how to factor an x squared. So I'm going to go x plus 2 times, I set it up x and x. I get, let's see, multiply to negative 6 and add to negative 1. I'm going to say negative 3 and positive 2. And now it's completely factored. And all the zeros are, or the roots, are now x equals negative 2, 3, and negative 2 again, which is a repeated root, so I don't have to write it down again. All right, so actually if I factor this, I want to say it like this. I want to say x plus 2 squared times x minus 3. I didn't notice those repeated roots there. All right, so here's another example that we can try. Actually, we've got 2 more to do. We're just going to do this second one here, and because this video is getting kind of long. All right, so what are the factors of the leading coefficient? That's our leading coefficient. The factors are 1 and 3. What are the factors of the constant? That's our constant, so 1 and 2. Don't worry about the negative, because in the end, we make our list positive and negative anyway, right? Like we did up here. We end up saying take the positive and negative combos. All right, so there's my leading coefficient. We want to also list the factors of the constant. This doesn't say that here. This is the factors of the constant. Those are going to be, like I said, 1 and 2. Now let's make the possible rational roots. So it's going to be the constant divided by the leading coefficient. So 1 over 1 is a possibility, if I do 1 divided by 1, or 1 divided by 3. Now I could do 2 divided by 1, or 2 divided by 3. There's all my combinations of fractions I can make that way. With the constant, right? It's this one on the top of the fraction, these on the bottom of the fraction. If I simplify those, 1 over 1 is 1, 1/3 is still 1/3, 2 over 1 is 2, and then 2/3. And it's going to be the positive and negative versions of all of those. So I've got 8 possibilities. So it says start testing and stop once you found one that works. I'm not going to make you test them and stop. We're just going to look at the graph to kind of cheat a little bit and see which one's going to work, and just make sure we pick one that works right away. Okay, so this is 3x cubed minus, I'm looking on my computer here, so you can type this into Desmos if you would like as well, or your graphing calculator, and see if you agree with me. Squared minus 7x minus 2. So I see it crosses the axis at 2, -1, and 1/3. That's the one we did before, -1/3. So it looks like your winners are, this is, again, I just want to write this over here because I kind of cheated, -1, -1/3, and 2. Those are all on my list, notice, right, because it's plus or minus. Start testing and stop once you find one root. So I'm going to use 2 because it's positive. And my leading coefficients were 3, -2, -7, -2. Remember, this is like if I plugged 2 in to the function and got 0. I'm looking to get a remainder of 0 since it works. I know it works. Drop down to 3. 3 times 2 is 6. 6 minus 2 is 4. 4 times 2 is 8. 8 minus 7 is 1. 1 times 2 is 2. That equals 0. So I did show that f of 2 equals 0, which means it is a root. All right. Now we're going to use the division algorithm of polynomials to start factoring this thing. So I know that this turns into the divisor x minus 2, and I know that my quotient turns into 3x squared plus 4x plus 1 with a remainder of 0. So my original function, which are we calling this one g? We are. G of x now factors into x minus 2 times the quotient, 3x squared plus 4x plus 1. So look at what we've done. Here was something that we couldn't factor by grouping. It was an x to the third. And now we've already factored out one linear factor. And now I'm left with an x squared, which means I can factor that through other methods. Actually, let me do this, because this one's going to be a split the middle term guy. So we're going to keep the 3x squared, and we're going to keep the plus 1. We're going to split that middle term. So we're looking for 3 times 1, which is 3. The factors of 3 that add to 4. It's going to be 3, and it's going to be 1. So we're going to call it plus 3x plus 1x. So we get x minus 2. And now if I common factor a 3x out of that and a plus 1 out of that, I get x plus 1, and here I get x plus 1. So finally factoring g of x, I get 3x plus 1 times x plus 1. It's completely factored, and the roots are whatever make these 0. So the roots are x equals 2 and negative 1. And how do I get this one? This one's a little trickier. Make it equal to 0 and solve. So I can subtract 1 and then divide by 3. So it's negative 1/3. Those are my roots, which I already cheated and found anyway up here. But you can kind of go through and prove it. All right, so we'll do some more practice with this next class.